Hi guys, we are starting a brand new unit. This is still considered a review unit. We will be talking about exponential functions and logarithmic functions. First, let's go ahead and get started with exponential functions. The definition of exponential function, as you can see on the screen, is any function denoted by a to the x power, where a has to be any positive number not equal to 1, and it is any real number. Right away we go into an example with sketching, but let's talk about this definition just very briefly. We do always want to look at a positive base when we talk about an exponential function. It is just a part of the definition. Part of it is the connection that we will be making with logarithmic functions starting the very next notes. However, for right now, just think about it as a part of the definition. We have one more condition here. It says that a cannot be equal to 1. The reason for that is, well, just think about what happens if this base is 1. Then you have 1 to the x power. Well, 1 to the first power is 1. 1 squared is still 1. 1 cubed is still 1. If we allow that base to be equal to 1, we're simply going to have a linear function. It's not of any interest to us, which is why we're not allowing that. Before we get to graphing, I want you to just think about that function for a minute. And I have this interesting Desmos to show you for it, to see if my mouse would actually listen to what I have to show you. So here I started by graphing f of x is equal to a of a to the x power. Please note that if you try to graph something like that, Desmos will automatically ask you if you want to add a slider. So I added a slider, and now I can change the value of a, because I want you to see what happens. So if I have a value of a is equal to 1, oh, I just have a horizontal line. That's not any fun. So I definitely don't want to have this value of 1. Well, what happens if I get a value bigger than 1? I'm going to zoom out here just for a minute. It looks like my function grows exponentially, and as the base gets bigger, it grows way quicker. Okay, let's see what happens when this base gets to be smaller than 1. Oh, look at that. The second it went over 1, the second I went right below 1, the function changed its direction. It looks like it is flipped across the y-axis, doesn't it? And here, the smaller that number gets, or the closer that number gets to 0, the faster the graph is considered to be decreasing. Something else interesting about this graph is that it is always either increasing. Right here, we have an always increasing function because our base is greater than 1. Where if the base was less than 1, then the function is constantly decreasing. It doesn't matter how far out we go, the function will never really cross the x-axis. It approaches it, but it does not cross it. Of course, we can do function transformations where that happens, but as of right now, this is not in our interest. So let's go ahead and look at an example. We are going to sketch the graph in the same coordinate plane. I'm not too fond of the examples that are on these notes. Let's go ahead and change those, okay? I know it says f of x is equal to 6x, but this is really hard to graph. So let's just do, I don't know, let's just do 2 to the x power. Okay? If you are not quite sure what values to input, it might be helpful to calculate a few of these values. Well, I know for a fact that 2 to the 0 power is going to be equal to 1. I know that 2 to the first power is simply 2. I know that 2 squared is equal to 4. I do know that 2 cubed is equal to 8. What happens when you have negative exponents? 2 to the negative first power is equal to 1/2. If we did 2 to the negative 2 power, then we have the reciprocal of 2 squared, which is 1/4. Now I can go ahead and graph some of these values. I have the point of 0, 1. I have the point of 1, 2. At 2, I have 4 because 2 squared is 4. 2 cubed is 8. If I want to do 2 to the 4th power, I will be somewhere all the way out here, maybe even higher, probably all the way out here. Well, when the values get smaller, I get half of 1, then I get half of that, then I get half of that, and I get really, really close to the x-axis, but never really cross it. Well, now I'm ready to go ahead and sketch that. Not the easiest job using the tablet that I'm using, but you get the idea. This is known as the exponential function. This here is my f of x is equal to 2 to the x. I'm going to change the color for the other function. Let's do green. Let's change that again. 12 to the x power. We can just put like 1 point on here. So let's change it to 4 to the x power. If it's helpful, go ahead and calculate a few values again. 4 to the negative 2 power is 1/16. 4 to the negative 1st is simply 1 over 4. As you can see, all of those values are positive, which is why we never really cross that x-axis. 4 to the 0 is equal to 1. Oh, look at that. For this function, I also have a point right here at 1. 4 to the 1st power is equal to 4. 4 squared is equal to 16. So already at 4 squared, I will be out of my graph. So here's 4 to the 1st. At 4 squared, I'm already out of the graph. 4 to the negative 1st, I could probably show, and everything else is just going to be really, really close to the x-axis. Okay, so it looks like as my base got larger, the function is increasing much, much, much quicker. Well, that makes sense, because each time I am multiplying by 4, where at the beginning each time I was multiplying my previous result by 2. I want you to please note that this value here, no matter what your base is, you will always have that value. Always, for any one of these bases, you will have a point that goes through 0, 1. Your next point will always go through the base and 1. A to the 1st power will always go through the base. Let's go ahead and look at the second example. For the second example, For the second example, we have to sketch the graph on the same coordinate plane. For this one, we can actually use the numbers given. So for example 2, I will go ahead and keep the bases as they are, but we want to see what happens when you have a negative in front of your variable. But wait a minute, don't we already know what happens? Isn't this here considered a transformation? Oh, maybe we should look back at our notes from Unit 1 and see what type of transformation that is. Okay, this will result in a flip across the y-axis. If you're not quite sure what happens though, just go ahead and do a table, get a few values in there, at least for the beginning. It is expected that you will be able to graph those relatively quickly and that you get the idea of the pattern, but at the beginning, tables are absolutely okay. So if we are looking at the x value and then f of x or y value, let's see what happens if you have -1, if you have 0, if you have 1, if you have 2. Okay? If you have -1, then you have 6 to the -1, which is simply 6 to the +1 power. It is just 6. 6 to the -0 Well, that's 1. 6 to the negative 1 is going to be 1/6. 6 to the negative 2 is going to be 1/36. Let's go ahead and plot those points. Once again, look at this. My point that will always be there, 0, 1, even though I have a negative exponent, I still have that same point of 0, 1. This time when I go to -1, I'm going to have a value of 6. Already the next value will be outside of my graph, of my coordinate plane. And this one is super steep. It is decreasing very, very, very quickly. Oh, I'm trying to not cross that line. It's not working very well for me. Oh, goodness. Yep, that's as good as it's going to get. So let's go ahead and look at the next one. You can once again fill this table out and get your values for x and f of x. Just be careful when you're doing your substitution. You have negative, and then you're inputting a negative x value. This will make it 12 to the negative 1, which is 12 to the first power, which is just 12. 12 to the 0 power is still 1. 12 to the first power is going to be 12 to the negative 1, which is 1/12. For this function, the green one, we still have that point that repeats no matter what. But then at -1, I am all the way up here, if I counted them correctly. This one is even steeper because the base is actually much greater than the first base. So it decreases even quicker. Decreases quicker or faster. Now, an important concept for our exponential function is this base of e. This is an irrational number, just like pi, but this one is e. It is equal to 2.7182818228 ... forever and ever and ever. Most of the time we do approximate this. We can use it as 2.72. However, your calculator has a button for e, so please feel free to use that button instead. We call this number the natural base. We will see it a lot with both exponential and logarithmic functions. So the function of f of x is equal to e to the x power is called a natural exponential function. Once again, it has this point of 0, 1, and then the point of 1 and your base, where the base is e. And then it has a few more functions. Once again, this value is approximately about 2.72, so you can calculate a few of these values if you were to graph it by hand.